This is going to be a short lecture covering section 7 of chapter 4, and we're going to go over how you can write something called ionic equations for reactions that occur in aqueous solution. And you should have already watched some videos from the textbook going over an introduction to some different types of reactions that occur in aqueous solution, as well as explaining how you can predict the products of a precipitation reaction and write an equation for that reaction. So please watch those videos first if you haven't watched them yet. But I'm going to start out just a review of that material. So we're going to go over how we write an equation for a precipitation reaction. So let's say you were to mix solutions of calcium nitrate and potassium carbonate. So what would be the products of this reaction? And let's write a balanced equation for that reaction. So remember, what can occur here is when you mix two solutions of ionic compounds, you can get an exchange. So the cation of the first compound can end up paired up with the anion of the second compound, and then the second cation can go with the first anion. So if I write out those two products, it would be calcium carbonate and potassium nitrate. And to balance that, I put a 2 in front of the potassium nitrate. So remember, don't write potassium nitrate as K2NO32. That's not the formula of potassium nitrate. The subscripts there after the potassium and the nitrate, they're just telling you you have 2 of each ion, so then that just becomes the coefficient when you balance the equation. So it's the products there, then calcium carbonate and 2 potassium nitrate. So the next thing you would do is go to the solubility rules and see if these compounds are soluble or insoluble. Calcium carbonate is insoluble, so that's the precipitate. So we write an S by it. Potassium nitrate would be soluble. Remember, compounds of potassium are always soluble. Compounds of nitrate are always soluble. So that remains in solution, so we write a Q after it. So again, calcium carbonate, the insoluble compound, that is the precipitate. And sometimes we put a downward pointing arrow just to emphasize that that's the precipitate, and we also rewrite an S after it. So that's the balanced equation for this precipitation reaction. When you mix calcium nitrate and potassium carbonate would precipitate. But you might notice that there is a little bit of a problem with this equation the way it's written, and that's because we learned in the last video lecture that when ionic compounds dissolve in water, they dissociate into their ions. So this does not show the ionic compounds as being dissociated. So in effect, we're treating these compounds as if they were non-electrolytes or just molecules. And so we can refer to this equation as a molecular equation. We're treating the substances as if they were molecules, even if they're ionic compounds. But we can rewrite this equation as an ionic equation. So what we do is to make this an ionic equation, any compounds that are electrolytes in solution, aqueous, then we dissociate them into their ions, just like we learned last time. Compounds, though, that are not electrolytes or precipitates, then we leave those just the way they are. We don't dissociate them. So anything that has a solid after it, so for example, the calcium carbonate here, we would not dissociate because it's only in aqueous solution that the ions are dissociated. In the solid state, the ions are still bonded together. Okay, so let's do this process then. Let's convert the equation above into an ionic equation. So I've written out that equation again. So what I'm going to do is I'm going to dissociate calcium nitrate into calcium ions, which is Ca2 plus aqueous, and then nitrate is NO3 minus, but I have 2 of them. So subscript after ions, then that just becomes a coefficient when we dissociate the ion, and then potassium ions, and actually there's 2 of them, so 2 K plus aqueous, and then carbonate is CO3 2 minus aqueous. So here I've taken the reactants and dissociated them into their ions. And then, now down below, I'm going to write the products. The products are calcium carbonate, solid, and then potassium nitrate. 2 potassium nitrates are going to dissociate into 2 potassium and 2 nitrate. Again, notice I did not dissociate the calcium carbonate. A trick to keep in mind is that anytime you have a free ion, so anytime you write something with a charge after it, it's always going to be aqueous. It's always going to have AQ written after it because an ion by itself like that can only exist in solution. A solid compound cannot be a single ion. Okay, so this equation is referred to as a complete ionic equation because it shows all of the ions that are involved in this reaction in the reactants and products. But you might notice that there are some ions that appear exactly the same way in the same number in both the reactants and the products. And we can cancel those. For example, we have 2 potassium ions in the reactants. We also have them in the products. So I'm canceling those. We also have 2 nitrates in the reactants and 2 nitrates in the products. The ions that we cancel, these are referred to as spectator ions. So the spectator ions in this particular example would be potassium and nitrate. So these spectator ions are not actually changing in the reaction. So we call them spectator ions because it's almost like they're just spectators. They're just watching the reaction and not taking part. So these ions do not experience any net change in the reaction. Now they do serve a function, and it's important they're there because the net change in this reaction is that aqueous calcium ions and carbonate ions are coming together and making calcium carbonate. The spectator ions are needed to balance out the charges of those ions. You can't just take a bottle of calcium ions and a bottle of carbonate ions and mix them together. Remember, ions don't exist by themselves. So the potassium and the nitrate ions are there to balance out the charges of the other ions before you mix the 2 solutions together. When you cancel the spectator ions from the complete ionic equation, what's left we call a net ionic equation. So we can write the net ionic equation for this reaction, but before we do that, let's just sort of go back to the beginning and go through all the steps again. So we started with the molecular equation. Calcium nitrate plus potassium carbonate making calcium carbonate solid, potassium nitrate aqueous. We dissociated all the aqueous compounds to get the complete ionic equation, and then we canceled the spectator ions, which were potassium and nitrate. And so when you cancel the spectator ions, what's left is the net ionic equation. And the reason why we use net ionic equations is because they clearly and concisely show just the net change that's occurring in the reaction. You don't have all these extra stuff to deal with. So the net ionic equation here, well, it's just going to be calcium ion, Ca2+, and remember always aqueous after an ion, plus carbonate, aqueous, precipitating as CaCO3 solid. So that's how we write the net ionic equation for a precipitation reaction. And notice there's a pattern here. What happened was the cation aqueous combined with the anion aqueous to give us our precipitate as a solid. And in fact, that's going to be the pattern for the net ionic equation for almost any precipitation reaction. Now there may be some balancing needed. In this case, just 1 cation plus 1 anion reacted to make 1 mole of precipitate, so we didn't need to add any coefficients. In some cases, you may need to add some coefficients, but otherwise, this is just a general pattern. Cation plus anion makes the precipitate.